Hello, we're going to do another example of double integration, and we're going to try and visualize while we do this what we are looking at. So we have a function of two variables and it's just y, so this is a plane, and then these bounds are giving us our rectangular region. Now if we think of this as being, z, a function of two variables, f of x, y, is just equal to y. Well, that's a plane. That's a plane that runs through the x-axis. And then if this were square, if we were thinking about z and y, would be perfectly diagonal. So I'm going to try and make that look the way I want it to in perspective here. So this is kind of my plane. And for example, we could think about this point right here as being 0, 1, 1. And this point right here would be 1, 1, 1 over here. I have 1, 0, 0, and then I've got 0, 0, 0. So this is my plane. And obviously it extends more than just this rectangular space I have drawn here. Okay, but we're going to calculate the region between, the volume between this region R, which is defined in XY. So defining that in XY, it's always helpful to draw our region. So dy first, that means these are in terms of y. I have the line y equals 1. Y equals 1 is my x-axis. This is my x-axis here, and that's y. And then I've got y equals sine x. So we've got our 0, and then y equals sine x. And sine x goes up like this, and it comes back down, and obviously it keeps going. But when I come through here and I look at my x values, since these guys right here, this is dx, this means this is x equals 0 and x equals pi. So we've got from 0 to pi. When I go to graph sine x, it just looks like this beautiful, not very smooth curve that I just drew, but I'm going to draw it again. So sine comes up here to 1. So now remembering this plane is extending out in all these directions and it's maybe coming out further here. And so now this is clearly not in scale. So there's my plane. And then I have this curve underneath representing my region. It comes up to 1, and then over here it might end at pi. So there's my 0 to pi on the x-axis and coming out to this value at 1. So kind of re-sketching this, we're going from 0 out here to pi. We have this curve that is the shape of sine x. And so that maximum, that comes over here to 1. And when you think about that plane, that diagonal plane slicing down through the region, it creates a wedge shape. I'm going to pause and draw it. So I'm not the best artist with this pen. It'd be much easier for me to draw on pencil with paper, but we have this wedge-shaped region. And this isn't drawn to scale because ideally that point, that max, is going to occur at pi over 2, and then my y is 1, my z is also 1. So we've got this wedge shape, and then this is of course at the origin, and over here this point is pi 0, 0. All right, so hopefully you kind of understand what I've done visualizing it. I think I've spent a long time doing that. Now let's just jump back to the original part of the problem and evaluate the integral. So the evaluation part of this isn't difficult. We're going to integrate with respect to y first. So that means I'm just doing this inner piece. And it's going to be 0 to pi, integrating y, that's going to give me 1/2 y squared. And of course that is from y equals sine of x to y equals 0. So we're going to plug those two values in, simplify, and then we'll look at evaluating the integral with respect to x. So plugging in 0, that's going to go away. So I'm going to end up with the integral from 0 to pi of 1/2, that's sine squared x dx. At this point, I need to understand or recognize how to integrate sine squared x, and probably the easiest way for us to deal with that is to use one of our double angle identities. So if I say 1/2 1 minus the cosine of 2x, that is equal to sine squared x. So I'm going to pull this 1/2 out in front, that 1/2 out in front. That's going to give me a 1/4, integral from 0 to pi of 1 minus cosine 2x dx. So using this double angle identity, that allows us to reduce the power. Once the power is gone, this is now two terms that are easy for us to integrate. So integrating with respect to x, that 1 becomes an x, and cosine 2x is going to be sine 2x divided by 2, or minus 1/2 sine of 2x, and that's from pi to 0. So we plug in pi, got this, we got pi minus 1/2 sine of 2 pi minus 0 minus 1/2. Sine of 2 times 0 is just 0. And of course, sine of 0 is 0, 0. Sine of 2 pi is 0. We end up with a solution, pi over 4. And so again, just to reiterate what we calculated, I've kind of tried to sketch this in here. We have this region formed by 0 to pi with a maximum of here at y equals 1. And so extruding that up and slicing through it with this plane, we get this wedge shape. As always, email me if you have any questions, but hopefully you're getting the hang of this.